Thank you, Sarah. So we start now the last session of this wonderful conference, and we open up with this Vincent Noireaux from Minnesota, University of Minnesota. And Vincent, the floor is yours.
All right. Thank you, Juan, for the introduction. I feel privileged to be here. I'd like to thank the National Science Foundation and the Bulgarian National Science Foundation for including me in the program of the conference. Thank you for still being here. It is the last session. We are going to close with my colleague Sofia just after with more biology. So what you see here, and I will return to this, those are the two examples that I want to discuss in the talk here. It's fluorescence microscopy. Some liposomes here are spherical and they become rod-like liposomes. I will discuss this first example and then I will go to this. You see also some fluorescence microscopy image where GFP is produced after some time, and those compartments that you see, they do not have membrane. They are membrane-based minimal cell system. That's it. So in one slide, I'd like to introduce what we do in my lab. Here is the most important thing is CFE, cell-free gene expression. We take the central dogma into some test tubes. That's it. We express genes, we make proteins, we synthesize proteins. And the goal here is that, in my lab, it's what we do. We construct biological systems outside living organisms using DNA program. That's it. And there are a number of applications to this, and many labs do this, by the way. Cell-free gene expression is becoming very popular as an experimental platform to build from the bottom up biochemical system and biological systems outside living organisms. So a huge activity is what we call prototyping. You can rapidly characterize prototype gene circuits or circuit parts like promoters, for example. There is another part of biotechnology. You can produce what we call biologics, therapeutics. Absolutely not related to that conference. More related to this conference is this one. It's synthetic life, and Dimitar yesterday introduced it. Synthetic biology enables building biological systems, and cell-free gene expression has become a very interesting and powerful experimental platform to build from the bottom up minimal cell systems. I will not talk about the phage synthesis. I will focus on minimal cells because it's directly related to this conference. So ladies, I'm going to focus on this. We encapsulate a cell-free gene expression system in liposomes, and we build up minimal cells like this. So it's a much more evolved system compared to proto-cell systems. So I will start with an introduction and go to some terminology and talk about the motivations and return to those two examples I was showing in the first slide: minimal cell systems and membrane-less minimal cells. And I'd like to acknowledge the work by the people. The first going from sphere to rod was done by David Garan. I will return to this. And Yannis is doing liquid phase separation with cell-free gene expression system, and of course the sponsor of this work. That's it. So here is the introduction. Let me go. You have heard that, especially today, about the terminology. So there are a growing community building synthetic cells from the bottom. So let me return a little bit to some terminology: protocells and proacells. What do the researchers do in that field? They synthesize cell size compartment using prebiotic molecules. They are going to use peptides, RNA, fatty acids. That's it. Those are protocells. Protos in Greek, it's origin. There is a minimal cell community, more or less does the same, using the molecules that you find in nature. We're going to use DNA, cell-free gene expression, the ribosomes, and phospholipids for the compound. And then there is the artificial cell community, more or less doing almost the same thing, but what we do here is we use natural and artificial molecules that are not found in nature. And the common point here, all of them are in some sort capable of some biosynthesis. That's it. The first example I will discuss, going from a sphere to a rod, is more a minimal cell system, and the second example, more related to the origin of life, is liquid phase separation, more related to protocell system. They are not exclusive. They are not exclusive. those fields, protocell, minimal cell, artificial, they overlap a little bit like this. They overlap OSR-based protocell with minimal cell with artificial cell. They overlap, they talk to each other on the boundaries, that's it. So what is experimentally, how does that look? We want to do some cell-free biology and biophysics in cell-size compartment. We want to learn bioconstruction in a minimal reduced system. You see it here, we want to work in a reduced setting at the scale of living cells, that's it. And we want to address challenging question, the origin of life or self-reproduction, that's it. It's what this community does, and eventually engineer biochemical system to develop new technologies. So you see what we do, we are going to work at the level of 1 to 100 micrometers, like already Vincent, and we are going to encapsulate material in the nutrients, molecular information, to make a compartment, some artificial components. It's what the people in this community, they do, and for example, protocell, once again, they use RNA or peptides. For minimal cell, we use a cell-free gene expression system, which is more complicated. And artificial cells, we use artificial components, that's it. So, cell-free gene expression. What is cell-free gene expression? Once again, becoming extremely popular. The number of articles every year is growing about cell-free gene expression. Literally, we have a liquid in a tube, and you clone your DNA, you put this DNA in your tube, in this liquid, and you make proteins. You recapitulate the central dogma in the test tube. I skip a lot of details there. We use DNA, linear or circular plasmids. And the transcription translation machinery, they are provided by a lysate. You prepare a lysate. It lasts a couple of days to prepare, and typically from E. coli, and you have your RNA polymerases and Noireaux to make transcription translation outside a living organism. It's a liquid. We have an ATP regeneration system, we activate glycolysis, we have all the nutrients, the amino acids, all the tRNAs, and the typical measurement we use GFP or other fluorescent protein. The cell-free gene expression system, they are very well described in literature, and they are even commercially available. What is it? What are the physiological properties? It's a cytoplasm. It's literally a cytoplasm diluted and taken from a living cell. You see, it's 200 to 300 millimolar salts, pH 8. We have 10 milligrams per ml of protein, including the ribosomes. It's a dilution by a factor of 25 to 30 times compared to E. coli. The viscosity is close to water, and there is no endogenous DNA mRNA. There is no genome there, there is no mRNA. There is just this liquid with the material for transcription and translation, and you clone your DNA, you put that in this system, and you synthesize GFP. You see myself here holding a tube. After a few hours, you synthesize GFP. You take the central dogma out of itself, and we are going to re-encapsulate this system and program a liposome towards developing a cell. That's it. It's called the minimal cell. And we learn bioconstruction. That's it. So the first example I was introducing in the first slide here is this one. So you see here the scale, we have liposomes, we use a soft matter physics technique to encapsulate the cell-free system. It is that in a test tube, now in a liposome at the scale of the cell. We express a cytoskeletal protein, and it took us a lot of time to understand why it does not work and how to make it work. That's it. So here is, I return to the minimal cell. We encapsulate the DNA, the cell-free gene expression system, in a cell-size compartment. Minimal, I say minimal from the beginning of the talk. Minimal towards the minimal genome size. It has been estimated that we will need 300 to 400 genes to make a liposome capable of dividing and reproducing itself. And we use, once again, the natural molecules, and we want to recapitulate some cellular function and go towards self-reproduction. You have seen this with one this morning, with Nikolai, I think with Thomas too. A cell is made in 3 parts: information, compartment, metabolism, and it has a unique property, self-reproduction. If you remove one of these parts, it does not work. If you remove information or compartment or metabolism, you don't get a living cell. So the idea is to integrate from the bottom up those 3 parts, using the cell-free gene expression system as a core. and liposomes. So we want to capture the cooperative links between those parts as we build them. And we want to determine what's necessary for self-reproduction. So we encapsulate, we are not in the tube. After a few hours, we express GFP. You see the self-gene expression system is there, we have the DNA, we express GFP, and you see this in the microscope. You produce GFP, it's dark outside. Why is it dark? Because it is the same as here, minus the self-gene expression system and DNA. We call that a feeding solution. We only express in liposomes. So we got interested in how to change the shape of this. When you do that, they are all spherical. How can we look like an E. coli or a real cell that is, you see that there's one axis longer than the other one. MREB, the protein MREB, is a cytoskeletal protein that makes E. coli as a rod, that's it. It looks like this, this is MREB and GFP. And when you look at the biology of it, it's complicated. This is MREB, it makes a filament, but it's coupled to many proteins, that's it. And when we decided to do it in the liposome, this is GFP again, and on this side we're going to see GFP and MREB fused together. We got this image, no deformation at all. We were not understanding. We tried all of those molecules, did not work. So we started to think it does not work either because we don't have an enzyme or it's something else. And we remember that a real cell looks like this. It's from David Good cell. This is the edge of E. coli. This is a ribosome there, the big purple things, and this is a membrane of E. coli. It's full of other membrane proteins. And so what we decided to do, we are going to express mRNA only, and we are going to emulate molecular crowding. We are going to put some polymers at the membrane. That's it. So here it is. We express those at the name of the plasmid, self-gene expression system. We have a membrane with nothing there. And here it's exactly the same, and we're going to put a membrane with polymers at the surface. And now it works, we just mRNA. We just add a polymer there, and mRNA self-assemble, and we go from the spheres to the rods. What is it? How does that work? Let me show the statistics first. This is the percentage of liposome, the radius, and as you go from dark to clear, we go from spheres to elongated shapes. So you see that without emulating molecular coding at the membrane, we are all spherical. With molecular coding at the membrane, we get the deformation, and the L over S is a long over short axis. And dark is a sphere, and clear is an elongated shape. This is a one-slide thermodynamics that explains what we see. You take A plus B in a chemical reaction, they self-assemble, you have your free energy. If you do that in the presence of macromolecules, here that there is only A and B in water, in the macromolecules, you get a delta of delta F, A plus B here is the same A plus B, but in the presence of macromolecules. What you do, be careful, is a delta of delta F. The delta, so delta FAB minus delta F 0, you get a positive contribution because it is entropically driven. When you self-assemble in the presence of macromolecules, you free some space for those macromolecules, and at the end, the thermodynamics tell you that you get a positive contribution. You are going to increase your constant of association. So it's purely thermodynamics, whatever you put at the membrane. Here we have PEG, by lipid pegs. We have done the same with other molecules. Here is a PEG again, this is the same system as before. We do the same with streptavidin, avidin, whatever protein that we stick to the membrane. You see the same. It's absolutely not about enzymes, it's about forcing self-assembly of mRNA, and it is based on entropy. That's it. It's entropically driven. In that case, we get the same statistics. We make rods at very small scale, and we stay like a sphere at large scale. The persistence length of those filaments are on the order of 5 to 10 micrometers, and therefore we deform at small scale. So you see that it's one example of this community encapsulating a self-gene expression system in liposomes, and trying to understand how we develop biological function and how we capture the relationship between the different blocks Here we express a gene, then it interacts with the membrane, and in fact it is not the enzyme pushing towards self-assembly and deformation, it is purely entropically driven, that's it. And we are continuing this work with other cytoskeletal protein, that's it, 5 minutes later. The last example I would like to discuss is this one, more related to the origin of life. We are trying to make liquid-liquid phase separation with a cell-free gene expression system. It's a very complex solution. As I was describing before, a lot of salts, a lot of proteins. And what you see here is what we are going to do. We are in a mineral oil and we make an emulsion. We have this cell size, the scale is there of the cell-free reaction, and we are going to shrink it by evaporating the water. And what we see a spontaneous phase separation appearing in the cell-free reaction. So very quickly, liquid-liquid phase separation versus co-accelerate, they are both liquid-liquid phase co-accelerate. When it's non-associated, you put polymers together, they do not associate, but the phase separate like this, it's just LLPS. A co-acervate is when you have a liquid-liquid phase separation, but there is a dilute phase. The polymer, they form droplets, and outside it's dilute. We are going to look at this just after. It is liquid-liquid phase separation. That's it. So here is what we do. It's a collaboration with Yusuke Maeda in Japan and his graduate student Shuzo Kato. We make an emulsion, and it's not liposomes here, it's mineral oil outside. And we have the cell-free reaction there. And we are going to evaporate the water to shrink these droplets. And concurrently, we express M-cherry and EGFP. So we have a cell-free reaction, and we evaporate the water, and we look at what's happening. So the cell-free reaction is emulsified, the volume of the droplet is decreased, we express M-cherry and EGFP, and we have a second phase. The cell-free reaction is by itself a phase of macromolecule. We have 2% in the system. And it's what you see after several hours. We evaporate, you see EGFP. It's shrinking. EGFP forms one droplet in this large droplet, and M-cherry colocalized outside, and here it is emerged. We observe both being expressed. And as the phases are formed, EGFP is going to form a droplet, and M-cherry is going to get outside of this droplet. So that is a potential mechanism of compartmentalizing biochemical reaction without membrane. There is no membrane at the surface here of EGFP between M-cherry and EGFP. And finally, I conclude with this one. There is another way to make liquid-liquid phase separation is with polymers. So here we do not shrink everything. We are going to add PEG and polyvinyl alcohol, and the third phase is a cell-free gene expression reaction. This is a phase contrast, and this is a fluorescence image. We have three phases here. The red is PEG, the continuous phase is another phase, and then you see those little droplets, it is a third phase of PVA, that's it. And I'm going to, so that is the EGFP, it starts to be complex, 3 phases. There is no surfactant there, no lipids, no nothing. And I'm going to return to MREP, this cytoskeletal protein, is what I was showing in the first slide. When we now express MREP, co-localized at the interface of those droplets. And once again, there is no membrane there. It's purely liquid-liquid phase separation. That's it. And so to conclude, with the minimal cell, we see that molecular crowding and entropy promote the polymerization of MREP without any additional enzymes, and we go from sphere to rod. And in the membraneless synthetic cells, liquid-liquid phase separation can be used to make membraneless synthetic cell, and we can also co-localize the self-assembly of cytoskeletal protein. In a broader perspective here, those experiments they show that macromolecules and crowding could have been critical mechanisms for the compartmentalization and shape of primordial biochemical reaction. That's it. And just one last slide, I'd like to make some advertisements. There is a synthetic biology summer course at Springer Laboratory every year. I have been instructor then, and I will return as an instructor next year in 2023. You see, it will be from July 26 to August 8. And here are the instructor, Carmela, Chris, Eric, and myself. And we are also invited speakers there. So for 2 weeks, you go to Cold Spring Harbor, and every day you do experiments on synthetic biology. If you want to learn about cloning, there is a module about cloning, many techniques about cloning DNA. There is a module about modeling gene circuits. There is a module on cell-free gene expression. I lead this one. You learn how to use a cell-free gene expression system, and you see what you can do with cell-free gene expression. You can do many things. The scalability of cell-free gene expression is huge. You go from the femtoliter to hundreds of liters. There's 18 orders of magnitude of scalability with the system. So if you want to learn biology, I just wanted to advertise this. It's a 2 weeks really intensive at the bench, and you do some experiment. That's it. Thank you for your attention.
Thank you very much.
So could you combine your two projects and use lipid-lipid phase separation-based subcompartments in a minimal cell, which is a normal vesicle?
So coupling both, we have not tried that. We could. I think that the lipids would immediately stabilize your liquid phase separation. You see what I'm saying? As long as you are going to put lipids, I'm afraid that they are going to go around those droplets and stabilize them.
But it doesn't happen in the real world. In the real world, you can get membraneless.
Yes, I agree with that.
So it depends on, you can put in specialized proteins that have the property of trying to make separate lipid phases.
We could think about that. It's something that we have not tried, but that's certainly a good idea for sure. Yeah.
Thank you.
Hey Vincent, great talk. Here I came in from NASA Ames Research Center. I have a question about your demonstration of a very elegant solution to controlling cell shape. Very simple. I was wondering if you could increase the elongation by within the elongated category by further increasing the overcrowding, or if it's more of a binary circular or rod shape.
Fantastic. Thank you for the question. You won't be able to do that because one of the limits there, you see, it works only at small scale. The persistence length of the filament made by MRIP, the persistence length is like the rigidity of those filaments, if you will. Is such that it's about 5 to 10 micrometers. After 5 to 10 micrometers, they become very flexible, and so they are going to just go around the curve of the liposomes, and you won't be able to push it further away and make very long rods. That's it. That is the biophysics that controls that. Yeah.
Next, right here.
Hi, Ajay from SPCA Paris. I wanted to ask what is the composition of salt in cell-free gene expression, and does it affect conservation?
So the composition you said of salt? Yes. So we have about 200 to 300 millimolar of potassium, which is physiological. We have about 10 millimolar magnesium. 10 millimolar magnesium and 200 to 300 millimolar potassium, which are at physiological concentration. It's what you find in cells. That's it. And what was the second part of the question?
Does it affect coagulation?
That's a very good point. We are working on that right now. But I would suspect that it does, absolutely.
I have another follow-up question.
Sure.
So when you are packaging, have you tried to study folding of the human cell?
Say that again, I cannot catch
Have you
it.
tried studying folding of proteins inside?
Well, I still cannot catch it, so maybe we discuss after. So I cannot.
Have you tried folding of RNAs inside?
Folding of RNA.
Yes.
Folding of RNA, what type of RNA?
Any kind?
Because we do transcription translation, so we produce a lot of RNA for sure. But we have not focused really on that. That's it.
Okay. Thank you.
Thank you.
Thank you. Please.
Hi, I'm Sucho from UT Austin. I have a nice question. So for the second part, for the liquid phase separation and synthetic cell, so is there any kind of optimal size of the your synthetic vesicle for having the optimal RNA synthesis inside?
So that's also a very good question. that is essentially controlled by the mechanics that you are going to use to break the droplets. Do you see what I'm saying? So I suspect that we could change the size of the droplet, but it's not something that we have yet fully investigated. But I suspect it's controlled by the mechanics of the energy that you put in the system when you create the LLPS. Yeah.
Yeah, just for the follow-up question in that direction. So thinking about the stability of this droplet, the droplets you're observing or tracking, are they like exhibiting some like a coalescence, like as the R synthesis is going, or in the opposite, like breakdown into 2 or 3?
It's relatively stable. It turns out that the LLPS that we make, the polymers that we make, the droplets are relatively stable in time. We have not really observed coalescence or droplets that fuse together.
Okay, I just wonder phase diagram. Yeah, the
Sure.
Just because. Thank you.
Okay, thank you. Yeah.
Any more questions? Something which is burning, that if you don't ask it, then you'll get sick? Okay? Okay, so if there are no more questions,
Thank you.
Vincent, thank you very much for being here.